precipitation reactions. So hard water versus soft water. It has nothing to do with how the water feels. Hard water contains dissolved minerals. The tap water in this area is hard water. If you live in the country and you have a well, you have like really, really hard water. So what makes it hard? Dissolved ions. Calcium ions, magnesium ions are the main ones. Question? Mm-hmm. Right. That's a good question. So a water softener, what does that do? And you can have potassium or sodium. So what they're doing with the water softener is you're exchanging calcium ions and magnesium ions for sodium ions or potassium ions. So I think what would be best is if you could get a combination of sodium and potassium, because your body uses both sodium and potassium to regulate the fluids. So if you get too much sodium, your body will retain fluid. If you get too much potassium, you're going to lose your fluid, so you need a balance. So it's, I would say probably half and half-ish, yeah, would probably be good. So softening water is a good idea. It makes a lot of things in your house better, but it does have drawbacks. Yeah. So, you know, if you've got someone who's got hypertension, needs to watch their sodium, and you're using a sodium-based water softener, drinking that water is not going to be good for them. Now, does that mean you can't use a water softener? No, but then that person should not be drinking the tap water. Should run it through, you know, a Brita or pure filter or, you know, buy bottled water. It would be better for them to use the potassium. And that comes into, you know, play in lots of things. Like potato chips are very salty, right? But if you look at the nutritional information on them, some brands like Lay's potato chips, there's a lot of potassium as well in the potato chips. And so the sodium with the potassium balances out and doesn't affect you as much as a brand that's got a lot of sodium and very little potassium. You know. So chemistry, a little knowledge of chemistry can be useful in everyday life. So what is it about these calcium and magnesium ions that cause a problem? Well, one of the things they do is they react with soap and they form a gray curd, is what they call it in the industry. We call it bathtub ring, soap scum, right? So you take a bath. Here, this is a colored bathtub or faucet sink, so you can see the stuff. If your tub is white, you don't really notice it as much. But after a while, you're like, there's this kind of gray ring around the bathtub. Yuck, what's that? That's the calcium and magnesium ions in the hard water reacting with the soap that you use. So this would not be a good thing to have happen in your washing machine, right? So if you use soap instead of detergent in your washing machine, this gray curd, scummy stuff ends up on your clothes, and especially your white clothes start to look dingy and gray because they're coated with soap scum, basically. So why is detergent better? It has sodium carbonate in it, which helps to get rid of the calcium and the magnesium ions so that they can't make that scum with the soap. So it forms calcium carbonate and magnesium carbonate. If we go through our table of things, we find that those are not soluble. The reactions that occur here, calcium ion plus carbonate ion, will form calcium carbonate. It's insoluble. It precipitates as a solid. It'll form little particles, and those will fall to the bottom. They'll precipitate. It's an example of a precipitation reaction. So we can define precipitation reactions as reactions in which a solid, also known as a precipitate, forms when we mix two solutions. So here's an illustration. Here we have a clear, colorless liquid. We're adding it to another clear, colorless liquid. It looks like we're adding water to water. And like magic, we get this yellow cloud. It's like, is that a genie? Is it magic? No, it'd be fun to think that. This is a precipitation reaction. It's forming a yellow colored solid. It doesn't look solid here because it's very small particles and they are floating around. We can tell it's solid because we can't see through it. The particles are large enough to obstruct light passing through. So if you can also mix two things and form a clear colored solution, that's not a precipitate. The cloudiness tells us it's a solid, it's a precipitate. And if you wait, that yellow stuff will settle to the bottom of the beaker or the flask. So what's happening here is we've got potassium iodide. So we've got potassium ions and iodide ions. And in the flask, we've got lead 2 and nitrate ions. Both of these substances, ionic compounds, are soluble. You can look them up in the table. When we mix these, though, the lead and the iodide ions can get together. You look that up, it's insoluble. Potassium and nitrate together is soluble. So a solid compound forms where there wasn't one before. That's a precipitation reaction. How do we know what the product is and which, what is the formula for that solid that forms? Well, you have to look at the ions that are originally present. So in the potassium iodide solution, we have potassium ions and iodide ions. And over in this beaker, we have lead ions and nitrate ions. So this plays into my feeling that metals are masculine and nonmetals are non-masculine or feminine. And they even color-coded these nicely. So this is the guy, the blue, and the pink for the girl. So these are like two, friends who are going to a party. They just didn't want to go alone. They're not in a relationship or anything. They're just going to a party together. And here's lead, and lead and nitrate are showing up together. Maybe they got a +1 invitation or something. Didn't want to go alone. Don't have a significant other. What are you going to do? You find a friend, somebody you don't hate, right? Take along. So they come to the party, and now all these ions are mixing together. So potassium meets nitrate. Wasn't exposed to nitrate before, which is just hanging out with iodide. Potassium meets nitrate. It's like, oh, hi, I don't hate you, you're okay, but there's no attraction, right? But when lead meets iodide, there's chemistry, right? There's this instant attraction, right? And so they're not going to just keep floating around. Or they're like, I just really am fascinated with this person. And that's those people that end up they find a couch on the back porch, and you don't see them the rest of the party. They're out there like sweet talking into each other's ears or making out or something, but they're just off by themselves, right? They took themselves out of circulation. So that's what happens in a precipitation reaction. We've got 4 different ions coming together. Now you have to have a positive ion with a negative ion because it's electrical charges that are attracting. You can't have potassium and lead getting together because they're both positively charged and they're going to repel each other. So that's not going to work. But you look at the possible partnerships and you see what happens. How do we know if one of these is solid or insoluble? Well, you write the formulas and then you look at the table of solubility rules, hopefully the one that's in your mind. And you predict that potassium nitrate is going to be soluble because all potassium compounds are soluble. I kind of think of potassium as one of those guys that, he's friendly to everybody. He's not looking for a relationship, so he's just not going to settle down with anybody. You look up lead iodide, and iodide compounds are generally soluble. So iodide is one of those women who's very picky. There's only 3 guys, silver, mercury 1, and lead 2, that she's going to go sit on the porch with. But here's lead 2, it's one of them. So that'll form a precipitate. You get a party together, like let's say we invite potassium with iodide and sodium with chloride to the party. Does this always happen where 2 people hit it off and become, life partners? No, doesn't always happen. there has to be the right combination of ions. So precipitations do not happen every time we mix two solutions together. It's only if one of the possible products is an insoluble compound. Then it's a precipitation reaction. So we need to learn how to write equations for precipitation reactions. If you're given two ionic compounds, you should be able to write an equation for a precipitation reaction that occurs. It doesn't always happen, but we can still write the equation. So the first thing you need to do is you need the formulas for the reactants. And then you need to look at the formulas of the possible products and decide, by referring to the solubility rules, if one or both of those are insoluble. If they are, then you've got a reaction. If both of the possible products are soluble, then nothing's going to happen. And so you write no reaction. So the arrow goes to no reaction. Nothing happens. They just mix together. It's not a chemical reaction. It's a physical change of mixing. If either of the products is insoluble, then you have to finish the whole thing. So you write the formulas for the products, and you indicate the insoluble one by putting S for solid. And if it's soluble, you put AQ for aqueous, and then you balance the equation. So let's do a couple of examples. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate are mixed. So we need to remember our nomenclature. So ammonium chloride, and we're going to do the same steps as we did in writing a formula for ammonium chloride, and we're going to write the individual ions with their charges. So ammonium is NH4, because that's what it is. Chloride is Cl minus. It's a chlorine atom become an ion. The charge is predictable from the periodic table. So we look at the charges on these two, and we put them together so that the charges would add up to 0. Here, we'll need one of each. Usually in a question like this, the reactants are soluble, but it's a good idea to check. So you check on the table, ammonium compounds are always soluble, so this is aqueous. Iron 3 nitrate. Well, iron 3 is Fe 3+. The Roman numeral 3 tells us the charge on the ion. It does not tell us how many. It's the charge. Nitrate ion is NO3 with a -1 charge, because we memorize it. That's just what it is. We look at the relative charges, whatever method you like, crisscross or least common multiple, and we figure out that this should be Fe, and we need 3 nitrate ions to balance that charge. Looking at solubility rules, nitrate ions, compounds containing nitrate are always soluble, and so that's aqueous as well. So there's our reactants. Now we have to look at the possible products and see, is there a precipitate? So we're going to swap partners. So ammonium came with chloride. We're going to see what happens when ammonium meets nitrate. Are they going to hit it off? Chloride came with ammonium, but we're going to see how she likes iron 3. So over here, again, I'm going to write the cation first and then the anion because it's convention. Just like on an invitation, it's Mr. and Mrs. Put the guy first and then the girl. No reflection on value of individuals. So NH4 plus, and I'm going to see what happens if that pairs with nitrate ion. And then I'm going to look at Fe 3+ paired with chloride ion. You could put Fe and Cl first and ammonium and nitrate last. That doesn't matter. So when these guys get together, would that compound be soluble or insoluble? What's in the first row of the solubility rules? Ammonium. All ammonium compounds are soluble. So that one's soluble. How about Fe and Cl? Remember the table? Chloride ions are generally soluble in their compounds, except silver, mercury, and lead. Well, this isn't one of those exceptions. So this one's also soluble. Both of these are soluble. There's no reaction. N, R. No reaction. Any questions? A physical change has occurred. There's mixing, but there's no chemical reaction. We haven't formed a new substance. Let's do another one. Write an equation for the precipitation reaction that occurs, if any, when sodium hydroxide and copper 2 bromide are mixed. So again, we're going to look at these names. Sodium hydroxide, we need the formula for those ions. So sodium is Na+. Hydroxide is a polyatomic ion that we memorize, OH-. Putting those two together, we've got +1, -1. Put those two together, we get NaOH. Sodium compounds are always soluble, so this is aqueous. Copper 2 bromide. Copper 2, that's Cu 2+, because the Roman numeral 2 tells us the charge is 2. Bromide is Br-. So we put those two together, we get CuBr2. And if we look in the solubility rules, bromide compounds are soluble. Copper is not one of the 3 exceptions, so this is aqueous. So that should be review. That's nomenclature, really. So we're going to swap these partners. We're going to mix it up here and see if there's chemistry. So we'll see what happens with sodium and bromide. And we'll see what happens with copper 2+ and hydroxide ion. So I'm evaluating the solubility of this. Sodium compounds are always soluble. This is soluble. That's going to be aqueous. Copper 2 and hydroxide. So we're going to make it all the way through the top half of the table into the bottom half of the table. Hydroxide compounds are generally insoluble, except strontium, barium, and hydroxide are slightly soluble. This isn't an exception. This is going to be a solid. So dang, we have to finish this one. You knew there'd be one like that at least, right? So to finish this, I'm going to look at the charges and write the formula for the products. So that's going to be NaBr. We already determined it's soluble, so we're going to put AQ. Copper and hydroxide, we're going to need 2 hydroxide ions for the 1 copper 2 ion, and we know that's a solid. Then we're going to balance the equation. So over here I've got 1 sodium, and over here I've got 1 sodium. Awesome. Here I've got 1 hydroxide. You see how this hydroxide ion, this polyatomic ion, stayed together? She came with sodium, and she's going to leave with copper, but it's still hydroxide ion. So over here I've got 1 hydroxide ion. Over here I've got 2. So that's not balanced. So I need to put a 2 in front of sodium hydroxide so that I can get 2 hydroxide ions. But now I screwed up the sodium, didn't I? Well, let's fix that before we forget about it. So 2 sodiums now. I need to get there to be 2 sodiums on this side, so I have to put a 2 in front of that one. So now I've got sodium and hydroxide taken care of. So let's look at copper. 1 copper here and 1 copper there. Nice. 2 bromines and 2 bromines. There we go. And that's how you do it. Any questions? Bunch of little steps put together. Is it easy to make a mistake doing that? Yeah, it is. Got to master the individual pieces before you can put them together. If you're having a hard time, like maybe I even gave you the formulas for the reactants, you need to be able to pull them apart into their ions and figure out their charges so that you can pair them up differently. If you can't do that, you're not going to be able to write these equations. So our stuff is building on itself now.